Hello. I have no idea if this is working. And I actually cannot see the chat here either. So I'm going to take a couple minutes to figure this out. Right now, uh, oh yes, here's the chat. So if anybody could let me know if this is working right now, and everybody can see my screen, and I'm screaming, and not just talking to myself, that would be nice. If there's people in here. Okay, good. There's somebody here. Um, so yeah, this is working. Uh, cool. Okay, we're gonna give a couple minutes to begin, maybe 1 minute or so. But welcome to this webinar. In terms of we're going to be doing a lot of fun stuff today in terms of building structural models with Grasshopper and Speckle in particular. Yeah, so this is mainly what we're going to be doing today. And hopefully by attending this webinar, everybody will have a more in-depth understanding of how to build structural models with Grasshopper and the Grasshopper components inside that we offer now support with Speckle. And this will hopefully help people build really cool parametric models with Speckle using our ETABS connector. So let's begin. So what is Speckle and how can Speckle help structural engineers? So first of all, I'm just going to go over the slide quickly in depth, but I hope that if you're attending this webinar that you do kind of know what Speckle is. That basically Speckle is basically a cross-vendor interoperability data platform for people. There's automatic revision tracking that is enabled along with it as well. And the point of Speckle for structural engineers is that it helps to, hopefully, is to help you to build better models. And you can share this data with people so that they can use it for their work. And by doing so, you can create a foundation for workflow automation. And this is probably the most important thing: is that Speckle is another automation. It's an automation tool. It's going to be helpful for structural engineers to build a very automation tool, and it's a powerful automation tool. In the past, during my internship at Arup, I often said that automation is measured by how much intern hours you can replace, and I still believe that. And I believe that Speckle can help structural engineers build parametric models in Grasshopper to ETABS in particular. So for this webinar, we'll be actually looking at the structural kit and using the basic structural model kit to send geometry, and we'll do some loading as well on top of that. And we'll also receive a model to kind of see what it ends up looking like, what a model looks like on the side of their in the side of the world of Grasshopper. We'll talk a bit about the ETABS and GSA specific elements, which is currently supported by the structural kit. And then we'll recap a bit later to kind of talk about how this all ties in together. So for this webinar, if you don't have already, hopefully you have Rhino and Grasshopper installed properly. I'll be using ETABS to demonstrate a lot of the structural model kits and kind of what they can do with that. A Speckle account on XYZ and a Speckle manager. And Speckle Manager to kind of open to kind of so that you can install ETABS from and have everything managed for your servers and your account. So to kind of actually give a bit of context behind of how the entire structural model is built, there's this structural schema, and this is really basically the Grasshopper schema is very heavily dependent on this, and so there's basic elements inside the structural components and kits, and these consist of nodes and elements, and we'll see them later as we go through them. And this is the way that we approach this problem, kind of how interoperability works between a lot of different software, is that there is these basic minimum information that required that each type of structural software, regardless of whether they're ETABS or GSA or Tekla, they will always have these types of elements in them. So nodes, for example, elements and releases. So these are common throughout all types of structural model, and this is what is being represented in the purple layer. The next layer is really these specific components that exist only between certain software. And there's so for example, in ETABS, you might have spandrels and pure elements, and this might be specific to ETABS, and you might not be able to have them in other software, such as GSA, for example. And by having components between this, you'll be able to have interoperability. And the hope is that you can build models more quickly without for developers to actually also build models uh, and build connectors. And this schema is always constant under revision. So as this webinar is being recorded today, you might notice that there will be classes changing as time goes on. And so now, without further ado, we'll probably get started in terms of the actual tutorial segment of this webinar. And let me turn out this aspect of it, and we'll go over to Grasshopper and structures. So here we live in the world of Speckle and Grasshopper and Rhino. And here we have this basic webinar starting file. I'll be sharing this webinar starting file inside on our blog post later with regards to this webinar. But we have a basic space trust frame that's generated with the Lunchbox plugin. This Lunchbox plugin, because I can't really actually build anything parametrically myself, so this is why I have this Lunchbox plugin. So you want to play around and follow along with me in this tutorial. Hopefully you do have Lunchbox plugin set up. And anyhow, before I ramble on too long, so in Speckle, we have a bunch of tabs here actually that are Speckle related, and you'll see the descenders and the created. And then you also have the Speckle to Speckle specific objects, which is going to have analysis, you're going to have geometry. And these are all basically what I was talking about before in the purple layer. And we're going to be using some of these components today to be building our entire structural model, and we'll go in depth one by one, kind of to start off with how we would build a model in ETABS. We're using this geometry with restraints and some loadings and stuff like that. So there's really seven main categories or so inside the main structural kit. There's analysis, which here we have a model information and all the information pertaining to the model. And then we have our geometry, and we have every single type of geometry that you have in here, from 1D elements to 2D elements to 3D elements, and nodes and restraints. We'll be using a lot of this today. And then we have our loading elements. So you can build your gravity load, your face loads, your beam loads and load cases. We'll be doing some load cases as well today for ETABS. And then you have your material, which you can define by the steel and concrete and timber, or you can have a custom material with specific properties. We'll be using catalog material today. Then you have your properties here, and you can have we have your 1D properties, 2D properties, and spring and mass properties and dampener properties that you can expect inside a structural model. Results here is kind of this you won't be using this to be sending to eTabs. You'll be generating results in eTabs. So this is really more for you to expand and see the results on the other side. And then we have the section profile, which you can define custom sections or use sections here. In kind of getting started in terms of we have some basic sections in here, including channels and I sections and rectangular, but in addition to defining sections from catalog. Um, so in addition to that, we also have elements pertaining specifically to each software. So you have here some Speckle to GSA connectors, and we have some Speckle to eTabs connector components, and we'll be using one the Speckle to eTabs components to define some more specific nuances that would exist only in the eTabs world. And the main point to keep in mind here, because as the principle behind building these models inside Grasshopper is to build them parametrically, of course, but to also to understand that the logic behind what is being presented here, or how basically a model is being built in Grasshopper using these components. So let's get started. So first, let's start with the analysis, because this will probably be the easiest thing. So the first thing we always want to do is grab an analysis model here, and we're going to just plop it down. And the reason why we want uh, this is the last element that we're always going to be sending to their connector in the end. So everything actually has to go through here. And you can see here we have the specs, we have the nodes, we have the elements, the load restraints and properties and materials. So everything actually kind of gets encapsulated in this model in the end before it gets sent to the Speckle stream and server. So we're going to start with some of the information about this eTabs model. So here we're going to be sending this to the specs and connecting it just like that. And here we can kind of put in our basic stuff about the engineer. So let's just put in some things like Reynolds for the engineering application, the engineering initials here. I'll put in some description for the project. Let's put in a project number. So let's put this 01. And then we're going to put in a project name for this. Let's say Speckle Space Truss. I'm going to connect that just like that. Cool. So having that being done, we can also put in settings now, right? So we can put in the settings, and if at any point we're confused as to what is required of the connector, you can just hover over the connector itself, and you can kind of see, okay, this requires a model settings component to be plugged into it for the next point. So let's just bring in model settings right here, which we have, and we're going to connect it just like this. So here we get to model settings, and we have a couple options here to put in and a couple things to fill out. So we have a model units here, first of all. So a model units, again, it's going to require us to, if we hover over it, we can see that it requires us to put in a model units section here. And we're going to actually go with custom here, because there is another option here that I don't want to use for today. But here, if you go and I'm going to pull this up and show this, we have an option built in here to use the metric or imperial. But I'm going to show you how to use custom, because I'm going to be exciting today. And I don't like that. Yes. Okay, so we have a model units here, and we're just going to connect it in here like that. And here we're going to specify some of the more important units that we would expect to see in eTabs. So for forces, let's go with kilonewton. That. For the length, let's go with millimeters. And then for the temperature, let's go with Celsius. Because we're going to use metric for today instead of imperial. Okay, so now let's go to the steel code. Oh, Lord. Okay, this mouse is terrible. But let's go to the steel code for setting this up. So for the steel code, so the question here might be, what do I put in here? This is a string text in here. And the answer is it depends on what the software you're going to be using for the application that you want to pull this into. For myself, I'll be using etabs, and I know that etabs has their steel code and their concrete code in this format. If I use their when I select their option from the beginning. So for their steel code, I'll be using this. Oh dear, copy and paste does not work sometimes. Be using the CSA as 1614. And then for the concrete code, I'll be using the other Canadian code that we have, which is just looking, because I don't remember this off the top of my head, CSA A23.3. Okay, so this helps us pretty much set up all analysis, kind of the beginning aspects of it. And it's pretty simple and straightforward, and you have a lot of flexibility. So let's just group that all together. And I'm going to pull that here and leave that by itself in here. So that's one aspect. Next thing we're going to do is we're going to create some elements. Okay. Here I have separated kind of already for convenience sake the web elements and the elements for the top and bottom flange. So I have these two separated already here. So I'm going to create 1D element here. I'm going to pick from local axis or orientation node. You have two options here. You can either build it from orientation node or you can build it from local axis. And here we pull out this. I'm going to pull out two of them. Okay, so I'm just going to connect this quickly to the baseline. So this is asking for a line element, which I have already here. I have 180 line elements. If you hover over here, it's asking for a line element for me to create. So I'm going to plot that in just like that. And I'm going to plot another one in like that. So the web elements, which we have here, we're going to classify them as a brace type for etabs. And then for the top and bottom flanges, for the top elements and the bottom elements of the space crust, we'll classify them as beam elements. Cool. Okay, the next thing we want to do is create some properties for this 1D elements. I want to create some 1D properties here. Cool. I'm going to create two. One for the top and one for the webs. And we're going to plug that in just like here, just like that. Okay, I'm going to create one catalog section here for, and then create the both of them as catalog section here actually, because I want to pick from the catalog of the Canadian sections here. And these are going to be steel elements. So I'm going to put that in here for now and plug that into profile. Okay, and here is asking us now for some material. So we're going to grab some materials from the material section. I'm going to create a speckle material here. And I'm going to just use steel because we're not going to use concrete in this building, this space cross at all. So we can plug them both in from here to here. Voila. Cool. So let's go to material and take a closer look into what we have for material. So we have all this, we have a name that requires a string, a grade, design code, and code year. And then we're going to have to put these in. So what do we want to put in each of these? So again, this depends on the connector and the software that you're connecting to in particular. In eTabs, there's a specific way of connecting, defining material, and I'm going to be using the method that's commonly used to define each one. So here in this case, we're going to call this steel, speckle steel. Oh dear. Because sometimes Grasshopper does not work. Okay. 1 second. Okay. Sorry, there's a bit of technical difficulty. I did not do this correctly. 1 second. Delete this. Okay. Speckle steel. And I'm going to give it the name over here. And I'm going to add in the rest of this stuff. And I'm going to have to look at my notes to kind of see what they are beforehand. So for the code year, we're going to use ASTM A992. And then for the design code, we're going to go with the Americans because in eTabs there's only an option to go with the, since I'm Canadian, actually, just for context, I'm a Canadian engineer, so we usually have Canadian material, but there's no Canadian materials in eTabs, so usually we define it directly from the American instead. So here we have the design code year, and the grade of the material, we're going to be using the grade 50. Cool. Okay, now we're going to be defining some catalog sections here. And giving some names to each of these. So we're going to actually use some classic I sections. In the Canadian sections, we call them W sections. So we're going to be using some W sections. And I want to call them directly from the catalog. So I'm just going to look directly at my notes and know that I already have a catalog section I can call. That's a W2 360 by 110. Cool. I'm going to do another one. I'm going to call this one W250 by 89. So for the catalog name, we're going to be using the catalog that we want to use, which in this case is CSIC10. So in etabs, I'll show later as we normally define what it means. This is the Canadian catalog that we'll be extracting from. And then for the section type, these are both I sections, so I'll always call them I, just like that. And then for the section name, this is the actual name of the catalog, the section that you want to call from the catalog. So you'll be using the name here as well that you had from before. So this is what's being pulled. This is kind of, if you imagine in etabs or in anything, you can kind of name the section to be something different. So this is the name of the section, but the actual section name is going to be the W250 by X89 or W360. Now we have the property here. We're going to call, for simplicity's sake, we're going to use these names over here to keep everything nice and tidy and well referenced. And I'm going to pull these guys in as well, like that. Cool. And now we are done. Elements. Okay. And we can just pull these guys in like right here. Cool. Now for the end releases, we can now actually define the end releases of these elements. And we can define them by, we can take the restraint and define them by enumerator. And so we're going to have fixed ends for all the fixed on both sides for all the members on the top. So for the members on the top, we're going to make them fixed on both sides. And then for the members on the bottom, we're going to make them a pinned element. And now this is getting messy. So we're going to move some space to give ourselves some space. So one side will be pinned. And if you ever use etabs, you know that a pinned element, for something to be fully pinned in etabs, one side is pinned, restrained on free rotational axis, and on the other side it's only restrained on the two rotational axis. So we can actually create something to mimic that in etabs. So we can create a restraint by code. And then on the other side, to mimic that pin element that we get, we can do it like this, and where we can now create an element. And if we hover over this, we can see that it requires a 6-character string to represent the restraint condition. So F equals fix, Y equals release, and there's an example of how to do it. All right. And so for our case, we'll be doing F, restrain, for the two last rotational elements to be restrained. And like so. Cool. This pretty much covers all the element 1D's elements. So we're going to group all that together and just hide it away from it now. Cool. Now let's move on to a 2D element. So here we have a specific property here that we can use. In particular, this pertains to the E-tabs. I want to create an unfilled deck with a steel deck membrane on the top, and then we have all the components that we would expect to see in the E-tabs. If E-tabs were ads prompting you for a definition of a steel deck, this is what it would prompt you as well. So these are all the same things that you would expect to see in the E-tabs world. So we're going to be pulling, this is a specific element from E-tabs, likewise. And then we have, to define our 2D element, we're going to go back to our general structural elements, and we're going to create a 2D element here. Like so. So here we have nodes, and this refers to the topological representation of a 2D element for now. So we need to create a bunch of nodes with the properties and the restraints. So here we have 4 nodes actually already inside from there. Okay, why is this being so annoying? Okay, here we go. Oh dear. Okay, that seems to do the trick. Okay, maybe I should have just made this maximized from the beginning. But, okay. So here we have actually 4 restraint nodes that define the entire square and the shell of our steel deck. And so we're going to actually take each of these nodes and create a node from it. What's important to note is that since it is a topological description of the elements, we do need to sort these nodes in a particular order. So we're going to have to create a sort element to sort the list of these nodes. This should go into value. And we're going to create 0. My Grasshopper is not behaving well today. We're going to create a panel. And we're going to kind of see what it looks like on the other side so we can know what. So these are the 4 points that define kind of the exterior. So we have to make sure that they're list ordered properly. So we're going to do them in the order of, right now we see them as 1500, 1000. So we actually want it to be like this. We want 2 and 3, so to be ahead first. And we want 1, 0 to be last. So now we see them, they make sense topologically. So it changes from one element. If you were a computer, you would imagine drawing a line from one line to the next. So you can only see while the coordinates changing one at a time. So this is one of the things we have to do a bit beforehand for 2D elements, which is the one thing that is a bit complicated. But um, this is only, we may change this in the future as time goes on. And now I'm going to create a nodes. I'm going to create them node with properties. And this ran out of error. Right, that's because I put in the wrong one. This is here. Right. And we're going to actually create a restraint for each of these nodes, like we did before, because we're going to fix all these points to be fixed in the model. And like before, we're going to create a restraint, and we're going to create call this to be completely fixed. Okay, so now we have 4 fixed points. And we're going to put these loads in here, just like that. And here we're going to define all the good stuff of our eTab deck. So we're going to make this, call it Speckle Deck first. We'll give it a name first. And we're going to use the same material from before. So for this case, we're going to use material from the steel section here. So we're going to be grabbing it from here, actually. And this is spaghetti now, which is okay. Okay. And we're going to be defining each of these little parameters. So deck thickness would be around 1 millimeter. I'm going to take a look at my notes I made before this to kind of see what I wanted the deck profile to be called. But so give me 1 second. So for unit weight, we're going to make it like so. The shear thickness is going to be 1 millimeter thick. The rib spacing is going to be 300. And then we're going to have the top to be 175, 125 for the top, and 175 for the bottom. And to make the rib depth to be 76. And the slab depth to be 87. Cool. Now that we have this defined properly, you can see there are certain things like etabs area string, so you could assign string elements to it as well, but we won't be doing that today. Cool. I'm going to plug this element. So this is a specific etabs element in this case. I'm going to plug it in here. So what do we have next to do? We have to create some loadings. So we're going to create a gravity load. And with a gravity load, we're going to define some load cases. Now in etabs, you know that for the gravity loads, each load case has a self-weight multiplier. So in this case, loading depends on really kind of how your model does it. But in the case of etabs, I know for a fact that the gravity load, each thing has a specific self weight factor. Each load case has a self weight factor associated with it. So if I'm going to create two load cases here, I'm going to create one dead load and one live load case here. You're going to have to create both gravity load cases for it. So in this case, I'm going to have to create one more in addition. And this is going to create the next load case here. And I'm going to create just like that. So the gravity factor, if it's just a dead case, I don't have to really worry about anything like that. I have to give it a name. I'm going to do this dead load speckle dead case. Speckle dead load. And then we have one gravity load just like that. And I'm going to create the next one. I'm going to call it live load case. And these are all permanent action type, as in these load do not change over respect to time. And then we're going to create a live speckle live load case here. Cool. So the gravity factor for the speckle live load case would be it's asking for a vector. In this case, we're going to create a vector from x, y, z components, and they're all going to be initialized to 0, which is the default initialization for here. I'm going to put these loads inside there, just like that. Cool. So this is the loading for the things. So now we have to actually put in let's put in a face load as well to make this exciting. So we're going to define a face load here. And we're going to grab the global. So this is the global direction. We're going to create this in the Z direction. And we're going to make this a constant face load across the steel deck. We're going to give it a value of negative 0.000 because this is, I put this in kilonewtons per millimeter squared. It's going to have to be a lot of zeros to adjust for that. So we're going to get that a value of something really tiny and small, about 1.5 kilopascal. And now we have to assign the load case. So we're going to put this to the live load case here, actually. We're going to assign that to the live load case here. And what else are we missing? We're missing the elements that is being applied to. And there you have it. You have one loading for the face load of the element to the elements. And we're going to plug that in here as well. And we have to actually flatten the load here because at the end of the day, we want only one local model, speckle model to come out. If we don't flatten this, it's actually going to create one speckle model with just the gravity loads and then one speckle model with the face loads. And now the only thing we're missing here is to plug in the rest of these elements here. So we're going to put in the nodes inside here that we created from before. Call that the nodes. And then we're going to put in the properties that the two 1D element properties that we created earlier. So here's the first one. If I could just get Grasshopper to work. Property 1 and property 2, we're going to plug in the material, which we have defined here. And then we have the property from above. Which is the deck property that we have defined here. Cool. And now we have one fully defined speckle object that's parametrically created that we can adjust the size and all the definitions of it geometrically and change all the components of it parametrically. For any of the components that I did not cover here today, you can always refer to our user documentation inside our Speckle website and for more extensive documentation to kind of see what is required of each component. Or if there's a lack of documentation per se, you can also contact the Speckle community forum. And so now we're going to send this to a stream. So if you've attended Alan's session and Alan's webinar, you would understand how to hopefully send Speckle data. So I'm not going to be covering this here. I'm going to create a stream here. I already have a stream ID set up here for myself. So I'm going to copy that in here. I'm going to send all that data to the Speckle world. And voila, the Speckle, you now have a Speckle model. And let's actually take a look at it before we go back to eTabs to see what it will look like. So I'm going to switch screen here for a second. And hopefully you can see here that I just pushed a new element here. And you can see that you do have indeed the model that we have. And if we inspect it and the elements inside here, we can see kind of the elements and the materials that we define in particular. So we define one material here, and it's a speckle steel and stuff like that. So now let's see if this actually works in eTabs, and we can put it in eTabs. So I'm going to save a new model, save this as a eTabs receive model from Grasshopper. I'm going to open up my Speckle connector here in eTabs. And I'm going to switch to the account that my Speckle screen is associated with. So it's going to be this one, which is the interop Grasshopper etabs parametric space cusp bottle here. And I'm going to click receive. I'm going to quick receive here. Illegal property. Yes, obviously the problem with live demos sometimes is that issues come up, and now I cannot close this, but I'm going to try this again. So we're going to receive this again, try. This is from a previous commit, so this is a commit I know I will work. Is there, because doing it live, I may have missed some points, but this is something, this is from another Grasshopper script in where I did the same exact thing. This is defined, and you can actually grab this off of Google Drive already. So this is exactly what it was from before. So actually, let's send this instead. This was sent to the same exact thing. Okay. So now we can see the refresh. Cool. And now we can see actually we have a fully built structural model here. We have the four screens on our side, which is the fix that we expected. These are completely fixed points. If you click any of the web elements in each house, you can see that they have the pin release that we expected. So like I was saying before, it was in each tabs, you know that only one side of the torsion is released completely. We see that all the web elements are defined by the W250 by X89, which is the one that we defined earlier. And then we have the W360 by 101 for all the elements of the top and bottom elements that we had. And we can even see that we have a Speckle steel deck defined, which is a defined section that we had from before. We can look at the loading on that Speckle steel deck. And we see that it's a live load for the live load pattern that we applied of the 1.5 kilopascal. And what else was there? We could see the load cases that we defined. So we have the dead load and the live load, which is defined from the Speckle. These are predefined in the etabs. And so let's try running it and see if it actually breaks. So we did save this model as etabs receive. And now we see that it works as expected. Yeah, and here you see the live load displacements that we had fun to find. So to recap everything, so so it's with any of these components that we have inside the Grasshopper world, you kind of want to actually kind of see what the structural software is expecting, and you can see that by actually the easiest way for you to do that. A big tip is for you to actually send a structural ETAS model to the Speckle server and kind of see, investigate, and play around with what each of the elements require and need to see what is expected. The documentation on a Speckle website is there for advanced usage. And by building models this way structurally, like parametrically, Speckle really enables you to actually have a really new way of kind of building all your models that you can get from Geometry Gym and other stuff. But the biggest thing about Speckle is that you have access to each of these data elements and collaboration. So uh, if there's any question and answer now in this chat, hopefully I didn't bore anybody, uh, but you can ask questions now, and hopefully this webinar was insightful for you. Or if everybody, I'm going to hang around for a couple minutes. Hey, so it doesn't look like there's a lot of live chat or anybody asking questions, so I'm going to end the webinar for today. So thanks for coming out. Hopefully this was insightful in terms of knowing how to set up a structural model. There was a lot of bit of hiccups in the middle because this is actually not how my normal computer setup is normally set up, but hopefully you had fun, and hopefully you can, if you have any questions, you can always ping us on the forum and set up, ask for help there. Have fun. Speckling.